So now we have two constraints, both of the form less than or equal. How would we write our Lagrange function? And how would we figure out the Kuhn-Tucker conditions? Who can tell me what our Lagrange function is? Somebody's whispering it. Was that you, Josh? Okay, you can go ahead and answer, Josh, even if it wasn't you. Sometimes people whisper, I can't tell who's doing it. X, Y. Okay, that's our objective function. That's what you want to write down first. That's the thing we want to maximize. Plus, right. Right. Yes. Right. Yes. This is just the way we want to write it. Here's our R1. Here's our lambda 1. G1 is the function x plus y, but we're subtracting it, so that's where those minus signs come from. We got a lambda 2, we got an R2, which is 40, minus G of 2, which is just x. Okay. So that's the Lagrange function. Then what is our Kuhn-Tucker conditions? What is partial z, partial x going to be? Anybody? What is partial z, partial x? Right. Y minus lambda 1 minus lambda 2. And we want this to be less than or equal to 0. Okay. Now, by complementary slackness, well, let me just go ahead and write it out. The rest of it would be this. Here's our non-negativity condition on x. And here's the complementary slackness condition. So I want to help you out here to make this easier. What would we assume about x in this case? What must the value of x be? The optimal value of x?
Not equal to 0?
It's going to be, yeah, it's going to be positive. Not equal to 0. The non-negativity condition said greater than or equal to 0. But you see if x were 0, that would be its lowest possible value. Then the utility would be 0. Surely we can do better than that. So let's just assume that the optimal value of x is positive. If the optimal value of x is positive, then what does that mean about partial z, partial x? Got to be equal to 0. So let's just guess that our optimal, that we don't have a corner solution in x. Okay. So let's just guess that partial z, partial x equals 0. So I'm going to erase all of this, and we'll write this. Now it could be that maybe when we solve for x and y, we might have to change that assumption. I think at this point it's a good guess that x will be positive. Because if x were 0, utility would be 0. Surely that's not the best we can do. Okay. But we might, if we find something different, we might have to go back and change that. But I don't think we will. Okay. What about partial z, partial y? Yeah, partial z, partial y would be, first of all, Zach, what would it be? Right. And that's it, because there's no y over here. Okay, so equals 0. And let's assume that the optimal value of y is positive. And by complementary slackness, partial z, partial y would have to be 0. So we're making a guess here, but that's a pretty safe guess. Now, what about partial z, partial lambda 1? partial z partial lambda 1 is just what? Yes. 100 minus x minus y. Now, by the Kuhn-Tucker conditions, this has to be greater than or equal to 0. Okay. And let's just leave that as it is for a moment. Lambda 1, of course, must be positive, greater than or equal to 0, rather. And then by complementary slackness, we must have lambda 1 partial z partial lambda 1 equals 0. And let's guess at this point that you spend all your income. Okay, that's a safe guess because the marginal utility of x, the marginal utility of y is always positive. So you're going to want to spend all your income. Okay, so if we guess the partial z, if we guess that you're going to spend all your income, then what does this equation become? In other words, we're guessing that the marginal utility of income is positive. And that means partial z partial lambda 1 is what? 0. So let's assume this is equal to 0. See, here's where the guessing comes in. Okay, we're assuming x is greater than 0, y is greater than 0. We're assuming that lambda 1 is positive, which means that, in effect, what that means is that constraint on income is binding. That's what that means. If lambda 1 is 0, the income constraint is binding. Then the final one is this, partial z partial lambda 2. And partial z partial lambda 2 is just equal to what? 40 minus x. Now here, you could make either guess would be plausible. Let's assume that we have to assume that this is greater than or equal to 0. But what I want to assume is lambda 2, which has to be greater than or equal to 0, is positive. So by complementary slackness, that means partial z partial lambda 2 equals 0. So if I assume this lambda 2 is positive, that means partial z partial lambda 2 is exactly 0. So let's assume this constraint is exactly binding. Let's assume lambda 2 is greater than 0. If I make that assumption, then this becomes exactly binding. Okay. This just becomes this. Okay. Now, some of these guesses may be wrong, in which case we'll run into problems. But I think all these guesses are reasonable. So from this equation right here, what do we get for x? If this equation holds, then x is what? 40. So right away, see, it's easy. X equals 40. Or x star, our optimum value of x is 40. Okay, now, what else can we do? Okay, we are assuming that this holds as an exact equality. So that means y star is equal to what? If x is 40, then y star must be 60. Okay? Notice those two values are both positive. So that means these assumptions are valid. Partial z partial x is 0. Partial z partial y is 0. Okay. All right, so let's go from this equation right here. What is lambda 1 star? What's the optimal value of lambda 1? 40. Because we already found x star was 40, so that means lambda 1 star is 40. That's positive. That's good. Had we found lambda 1 was negative, that would be bad. What that would mean is one of our guesses that we made earlier is incorrect. So we got to go back and fix that. We got to change that assumption. Okay, so it looks like we're so far so good. But we've got just one more variable. Lambda 1 is 40. So what is lambda 2? We got y star is 60. So what is lambda 2 star? Yes, it is 60 minus 40. That's 20. So lambda 2 star must be 20. That's good. See, now we've satisfied all the Kuhn-Tucker conditions. Both of our Lagrange multipliers turn out to be positive. That means both of these constraints, this constraint and this constraint, are exactly binding. They hold as exact equalities. And our partial z, partial x is equal to 0, partial z, partial y is 0. So we satisfied all the Kuhn-Tucker conditions. So that's the optimal solution. Okay. The optimal solution is this. X star equals 40. Y star equals 60. Lambda 1 star, just to repeat, lambda 1 star was 40. And lambda 2 star is 20. Okay. The interpretation of lambda 1 and lambda 2 is the same as before. What does this lambda 1 star of 40 mean? Go back to here. What does the fact that this is 40 mean in words? Have you forgotten the interpretation of the Lagrange multipliers? Right. Yeah, it's just the marginal utility of income. If your income went up by $1, your optimal utility would increase by 40 utils. What is the interpretation of lambda 2? Notice lambda 2 was equal to 20, wasn't it? What would be the interpretation of lambda 2? Exactly right. Exactly right. It's just how much extra utility you would get if this constant was increased by 1 unit. So if the government allowed you to have 41 units of X rather than 40, your utility would go up by 20. Okay. So in this example, all our guesses were correct. Let me just change this problem slightly and illustrate what can happen if you make an incorrect guess, because that'll happen. It's really a trial and error procedure. That's why it makes it interesting. Suppose I just change this as follows. Suppose the government says that you are allowed to have 60 or less units of good X. Then we go about solving again, and we would do the following. In this case, I'm just going to make a wrong guess in one case. Again, this is going to be the same. This, we change this from a 40 to a 60. Now I'm going to make the same guess as I did before. X is positive, Y is positive. We don't have a corner solution. That's reasonable. Because you could see if either x or y are 0, your utility is 0. We know we can do better than that. Let's assume both of these constraints. Lambda 1 positive means your income constraint is exactly binding. Lambda 2 positive means this constraint here on consumption of x is exactly binding. So then these equations would be the same. Okay. Partial z, partial x is still the same. Partial z, partial y is still the same. Partial z, partial lambda 1 would just be this. Now let's assume that your income constraint is exactly binding. That's what we assumed before. So then this will be exactly equal to 0. But let's assume that this constraint is also exactly binding. So that means partial z, partial lambda 2 is 60 minus x equals 0. We solved before, just as before. So now we get x star equals 60. Okay, that's positive. That's good. Substituting x star equals 60 here, you get y star equals 40. Okay, so far so good. Then what do we get for lambda 1 star here? Help me out. What is lambda 1 star going to be from this equation? 60. Okay. All right. Then we have y star. This is 60 now. Y was what? 40? Uh-oh. We got a problem, don't we? Because 40 minus 60 is minus 20. That means lambda 2 is minus 20. Okay. So that's a problem. Whenever you get a negative lambda value, that means you made a mistake in one of your assumptions. We didn't mathematically make a mistake, but one of our assumptions is wrong. And what was the assumption that was wrong? Yes. Let's replace that with this. Because the Kuhn-Tucker conditions only require that this be greater than or equal to 0. And the rest of it, of course, lambda 2 has to be greater than or equal to 0. Lambda 2, partial z, partial lambda 2. Complementary slackness, that must be 0. So in other words, let's assume that x, the optimal value of x is less than 60. Then what that means is lambda 2 will be 0. This term, partial z, partial lambda 2, assume that's positive. Then lambda 2 must be 0. Okay, now let's go back with that assumption. Okay, so lambda 2, we're assuming lambda 2 is 0 now. Because this led to a contradiction. So let's change this assumption. Keep all the other assumptions. Let's assume lambda 2 is 0. Then, let's look at that first equation. Lambda 2 is 0. So lambda 1 must be equal to y star. Lambda 1 star and y star are the same. And notice here what we get in this case. Lambda 1 star is also equal to x star. So now you get y star equals x star. Now, if y star and x star are the same, then from this one we get 100 minus 2x star equals 0, x star equals 50. And we assumed x star and y star are the same, so y star is 50 also. Okay. Then, let's see. Well, yeah, all of them are satisfied now, aren't they? Oh, the only thing is, we've got to check this one. If x star is 50, partial z partial lambda 2 is 60 minus 50, which is 10, and that is greater than or equal to 0. So all the conditions are satisfied. So that would be the solution. So graphically, the solution would just be this. It would be our traditional solution. Because this constraint, this rationing constraint, it's not effective at all. So here you go, x, y. Here's our budget constraint. And our budget constraint goes from 100 to 100. And we're on this budget line, consuming where x and y are both 50. Now, the other constraint is x less than or equal to 60. So here's x equals 60. But see, our optimal value was to consume only 50 units of x. So this constraint is satisfied because we're consuming less. But the lambda 2 value is actually 0 here. For the original problem, remember, was x less than or equal to 40. So for the original problem, it would look like this. 40 would be over here. And then what you want to do is consume at this point right here. Well, our original problem was x less than or equal to 40. So you're consuming at this point right here. Okay. So you're on a lower indifference curve. Okay. Now the constraint is actually binding. Okay. You're consuming right at 40. You get a lower utility in that case. Okay. Does that make sense to you? Okay. Let's consider a problem that's slightly more complex and one that is of relevance to the next homework problem set in 641. I'll modify it a little bit. Actually, I don't want to do the homework problem for you, but I'll go over a similar type of example. Let's continue using the same utility function. Maximize the same utility function. And let's use the same constraint for income. Same price of x, same price of y. But now, in order to consume each unit of good x, you have to pay a dollar price as well as a coupon price. Okay. The total number of coupons is given by a big C. The total number of coupons, say per month, is 120 coupons. Each unit of good x, call it C sub x, cost